Bismillahirrahmanirrahim. Welcome to a new lecture of discrete mathematics. Today we are going to study about Boolean algebra. So Boolean algebra, one thing I have to be in mind, because in most interviews the examiner asks about the Boolean algebra, is it a linear or non-linear, how is it? So in a discrete mathematics we can say that a Boolean algebra is a linear one. Okay, so coming to logistics, like in a Boolean we have a binary number, we have a base conversion, we have a number system for a negative number like a complement. We also have analog, digital analog conversion. So in a today lecture this can like a enzyme, useful law and theorem and example. Boolean algebra, we have like one thing is people we are studying like 1 2 3 4 5 6, we know about it, and for 1 2 3 4 5 6 and so on we can have some operation like add, multiple, subtract, division, etc. So in a same wise in the Boolean algebra, the operator like 0 and 1, we have a number there, and we have operator that how computer can add, subtract, multiply, divide and so on. I have the same operation as well there. So the enzyme law or theorem, so he said that we need to know some rule about how those 0 and 1 can be operated out on together. They are similar axiom to decimal number algebra, and there are some laws and theorems that are good for you to use to simplify your operation. So how does Boolean algebra fit into the big picture? It is a part of a combinational logic topic, different from the sequential logic topics. So learn enzyme and theorem of Boolean algebra allows you to design a logic function, it allows you to know how to combine different logic gate, allow you to simplify and optimize on a complex operation. So one thing about a Boolean, you already studied it in your architecture, in your DLD, in your introduction to computers. The same thing is here, but just here is just some like in a according to mathematics how it can work. So one thing you already studied that. Okay, so it's not a big deal for you guys. So coming to a Boolean algebra, a Boolean algebra comprises a set of element P, binary operator plus dots, unary operation like complements, and the following axiom: the set B contained at least two elements A, B with the A not equal to B. So the closure property like A plus B is in B, A dot B is in B. Then we have a commutative property A plus B is equal to B plus A, or A dot B is equal to B dot A. Associative property like A plus B plus C is equal to A plus B plus C, so this is called commutative property with respect to addition, commutative property with respect to multiplication, and the associative property with respect to addition, associative property with respect to multiplication. Then we have identity. A plus 0 also is 0. So what should be the identity in the addition? It is 0, and a multiplication we have a distributive law. So distributive law with respect to multiplication, distributive law with respect to addition, complementary. So these all the laws are we need to have in our Boolean algebra when we are solving our logical circuit. So we need to have these kind of a concept in our mind to use it and to find out the result of the circuit. Then coming to digital or binary logic in a Boolean algebra. So substitute 0 1 for B. So AND operator use a dot, OR operator use a plus, not for this one. Then Boolean product, Boolean sum, complement. So you guys remember that we studied in a lecture 1 about conjunction, disjunction and negation. So the same thing is for and we use a conjunction, for or we have a disjunction, and for not we use negation. Okay, so this is comparison now. Totally you are comparing your lecture number 1, which is totally based on discrete maths. So now compare that one with the Boolean one. So simple, this one is compared to and, this is compared to or, this is compared to not. So all the axiom hold for a binary logic. So definition for a Boolean function that maps input from the set 0 1 to the set 0 1. Simple. You have an input 0 or 1, then the output will be 0 or 1s, as you saw that in your digital logic designing circuit or a subject. Now coming to Boolean expression, an algebraic statement of a Boolean variable and operator. So now coming to this, logic gets and using operator and or not and a truth table. So once we have a AND operation, so x dot y, and for an AND operation we need to use an AND gate, and we will have a AND truth table. So in AND gate, once one of the input is 0, the output will be 0. In an OR gate, when one of the input or 1, the output will be 1. And the NOT gate is just like a complement. Once we have a 0, the output will be 1. When we have a input 1, the output will be 0. Logic function and Boolean algebra. So any logic function that is expressible as a truth table can be written in a Boolean algebra using a plus or dot, or this one. So xy, so az will be equal to x dot y using AND operation. This is using a x is equal to z is equal to x complement dot y. So again the same one. Then we have a x y, x complement y complement x dot y, x complement dot y complement and z. So the same concept is applying here, and you always study that in your DLD. So coming to some notation for the priorities. So a complement dot b plus c. So how we can solve this kind? So first of all, what we can do, we will solve the complement. So complement will have, then what we can, then we solve the complement with the AND operation, then we will add it. So variable and their complement, or sometimes called letter. So two key concepts, duality, like a meta theorem, a theorem about the theorems. All Boolean expressions have a logical duals. Any theorem that can be proved is also proved for its dual. Replace dot with plus, plus with dot, 0 with 1, and 1 with a 0. Leave the variable unchanged. This is about like a duality theorem. Then we have a De Morgan theorem. So procedure for complementing Boolean functions: replace dot with a plus, plus with a dot, 0 with a 1, 1 with a 0. Replace all the variable with their complement. Here was leave the variable unchanged, but here replace all the variable with their complement. So this is the difference between duality and a De Morgan theorem. So some useful laws and theorem: identity with respect to addition and with respect to multiplication. Then null and importance and evolution, complementary, commutative, associative, distributive, and uniting. So this is about duality. Okay, so hope you can be all memorize it. Then again we have some other useful laws and theorem, absorption, and then we have absorption 2, De Morgan, duality, multiplying and factoring, proving a theorem. Example 1, prove the uniting theorem x dot y plus x dot y complement is equal to x. So distributive, complementary, and identity. So what does it mean? What is the common between two? So x is a common, move it out. Then y plus y complement. So when y plus y complement, this will always be equal to 1. Okay. Then x dot 1 with x. So this is the proof. Example 2, prove the absorption theorem x plus x dot y is equal to x. Again the same one. So we can be used at x dot 1 and x dot y with it. So what is the common between 2? X, 1 plus y. So 1 plus y with identity 1. So which is x. Again, because it's already available here. So just memorize this. Once you memorize it, then you will understand it. Yeah, and how we can prove. Then prove example 3. Prove the consensus theorem xy plus yz plus x complement z and so on. So again the same thing is apply here and rearrange it. And coming to De Morgan theorem. Use De Morgan theorem to find a complement. Example, f is equal to a plus b bracket dot a complement plus c. So f complement a complement dot b complement. So we have this kind. So a plus b and c. How many variable we have? 3. So a, b, c. Then make it 0, 1, 2, 3, 4, 5, 6 up to some. Then again 3 here. So 0, 1, 2, 3, 4, 5, 6, 7 and so on. Okay. So what we can do, we need to find f first of all. So a plus b and c. Okay. So what we can do, so you know a plus b, then you can find a complement. So if you remember how you can solve, so first of all you need to find a plus b for all values. Then you can find a complement plus c, then add the value, then you will have your f. And the same thing here again. First of all you can find a complement, then find b complement, then find the c complement, and then add it, and you will have your required answer. Okay. So this is about your De Morgan theorem. So one more example of logic simplification, like example z is equal to a complement b c plus. So once this equation can be get from your circuit diagram. Once you have a AND or NOT gate or exclusive OR gate with the combination, then at the output you will have this kind of a equation. So how you can solve it out according distribute to complement distribute and law. What is the constant? Take a common it and find out. So the result will be bc plus a. So this lecture was really easy and you already studied it. So if I give you this kind of, hope you guys can also draw the circuit diagram as well, because it's totally based on a circuit diagram. And you studied it in digital logic designing, how you can design the circuit, how you can use combinational logic circuit like AND or buffer, exclusive OR, and make a designable circuit. Like you studied like what can I say, in a flip-flop as well, in a counter as well. So that was totally related to your digital logic designing. So by the way, so you guys watch this lecture, and if you have any question, you can't design the circuit, or you can't make any equation like this, so you can ask it. So and I will try to solve one of the example to that how we can design the circuit or how we can get the equation from a circuit. So I will help you in this section. So thank you for your time. See you in the next lecture.